In this lecture, we're going to give the proof of the Jordan Normal Form Theorem, which is the most difficult result in this course. We will begin with two auxiliary lemmas. Lemma 1. Let B be a linear operator on a vector space V, and let V1 through Vs be vectors in V. Fix some natural number m and consider the quotient space V by the kernel of b to the power m. Then the classes of these vectors of V1 through Vs are linearly independent in the quotient space, if and only if vectors b to the power m V1 through b to the power m Vs are linearly independent in V. Let's give a proof. Let's apply the first homomorphism theorem to the operator b to the power m on the space V. This theorem states that there is an isomorphism between spaces V quotient by the kernel of b to the power m and the image of b to the power m. The correspondence between these two spaces is given in the following way. So a class of a vector V is being mapped to the image of V under b to the power m. The first homomorphism theorem says that this is a linear transformation and an isomorphism. We know that isomorphisms preserves linear dependence or independence. And this gives us immediately the claim of this lemma, that the set of classes V1 through Vs is linearly independent in the quotient space on the left, V quotient by the kernel of b to the power m, if and only if the corresponding vectors in the image space are linearly independent. So the vectors b to the power m V1 through b to the power m Vs are linearly independent. In the Jordan Normal Form Theorem, we deal with strands of vectors that form bases for cyclic subspaces. To see how we can apply this lemma, let us consider the case where we have several strands of length m plus 1. When we apply operator b, we move down in each strand. And when we apply b to vectors at the lowest level 1, we kill each of these vectors. The kernel of b to the power m will be spanned by all vectors on this diagram except for the vectors that sit on the top level m plus 1. Then lemma 1 says that the classes of vectors v m plus 1, 1, dot, 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 v m plus 1, s are linearly independent in the quotient space if and only if the vectors at the bottom, so if we apply b to the power m to the top vectors, we get vectors at the bottom. So we get vectors v11 through v1s are linearly independent in V. This is the interpretation of lemma 1 in terms of these strands. Our next lemma will also be about linear independency of vectors in these strands, but now we will allow strands of various lengths. Consider a family of strands, like on this diagram. So here we recall that in notations Vij, so the first index I is the level of a vector. And the second index j is the index of a strand, so that we can distinguish different strands. When we apply operator b, we move down in each strand. So this means that b applied to vector Vij produces the vector vi-1j. So this is provided that I is greater than 1. And in case when I is equal to 1, when we apply b to the vector 1j that lives at the bottom level, then this is equal to 0 vector. So vectors on level 1 are annihilated by operator b. Let us now state lemma 2. Let Vij be a family of k strands of various lengths. Then the set of vectors in the strands Vij is linearly independent if and only if these are vectors v11 through v1k are linearly independent. This lemma says that if we just know that the set of vectors at the bottom level are linearly independent, then the whole set of vectors in all of these strands will be linearly independent. Since it's easier to formulate when a set of vectors is linearly dependent, we will actually be proving the statement that the set Vij is linearly dependent if and only if the set of vectors at the bottom layer v11 through v1k is linearly dependent. The backward direction here is immediate, since a set containing a linearly dependent subset is linearly dependent itself. So if we know that the smaller set at the bottom, v11 through v1k, is linearly dependent, then this implies that the larger set of all of these vectors in these families is also linearly dependent. Now let us prove the more interesting forward direction. So we assume that the larger set, Vij, is linearly dependent. Then there exists a family of scalars, Cij, not all 0, such that the sum over I and j, Cij times Vij is equal to a zero vector. Let CPQ be a non-zero coefficient with the highest possible value of p. This means that for I which are greater than p, all the coefficients Cij will be 0. Then we can drop all the terms with I greater than p from the sum, and we're going to get that the sum I goes from 1 to p, the sum over j, Cij times Vij is equal to a zero vector. Next, we apply operator b to the power of p minus 1 to both sides. Then we get that the sum I goes from 1 to p, the sum over j, Cij, b to the p minus 1, Vij is equal to 0. Here, if I is less than p, then b to the p minus 1 applied to Vij will give us a 0 vector. Since if we have a vector that sits at level p minus 1 or lower, by applying b to the p minus 1, we will annihilate that vector. And if I is equal to p, then b to the p minus 1 applied to Vpj is equal to V1j, a vector at the bottom level. So in this sum, we can drop all the terms with I less than p. And then we're going to get that the sum over j, Cpj times V1j is equal to a 0 vector. But here, the coefficient Cpq is not equal to 0 by our choice of this coefficient. And this implies that the set of vectors at the bottom, v11 through v1k, is linearly dependent. So this lemma says that if the vectors at the bottom level are linearly independent, then the set of all vectors in these strands will be linearly independent as well. The Jordan Normal Form Theorem states that for a linear operator on a finite-dimensional complex vector space, there exists a basis in which the matrix of this operator becomes block diagonal with Jordan blocks on the diagonal. Let us reformulate this theorem in terms of cyclic subspaces and the corresponding strands of vectors. So we have Jordan Normal Form Theorem. Let T be an operator on a finite-dimensional complex vector space V. Our first claim is that V decomposes into a direct sum of root spaces. So V is U lambda 1 plus U lambda k, where lambda 1 through lambda k are eigenvalues of T. This part is also known as the root decomposition theorem, which we already proved. And each root space may be further decomposed into a direct sum of cyclic subspaces with bases. So for each cyclic subspace, we have some generating vector v, and then t minus mu times I applied to v, t minus mu I squared applied to v, and t minus mu I to some power k applied to v, with the property that if we apply t minus mu I one more time, so k plus 1 to v, then we get a zero vector. This basis of a cyclic subspace is our strand, where the last vector is the bottom vector, which is the eigenvector for t with eigenvalue mu. The space spanned by these vectors is t invariant, and the matrix of t in this basis is a single Jordan block with eigenvalue mu along the diagonals. Since we already proved the first half of this theorem, it is sufficient to show that each root space has a basis which is a union of these strands that correspond to cyclic subspaces. Let us recall the algorithm for constructing these strands that we discussed in the previous lecture. Algorithm for constructing a Jordan basis of root space U mu. We construct the strands of vectors iteratively starting with the longest possible strands. Now let us describe in detail one iteration of this algorithm. How to construct strands of length n. We assume that we have already constructed strands Vij, where j goes from 1 to s, so we have s strands of length greater than n. Now, if we take vectors at level n in these previously constructed strands, then the set of equivalence classes of these vectors, Vn1 through Vns, is linearly independent in the quotient space, kernel of b to the power n, quotient by the kernel of b to the n minus 1. To construct top vectors in strands of length n, we complete the set of equivalence classes Vn1 through Vns to a basis of this quotient space of kernel b to the power n, quotient by the kernel of b to the n minus 1. here the operator B is T minus mu times I. So if the set Vn1 through Vns and then extended with Vns plus 1 to Vnr is a basis of this quotient space, kernel of b to the power n by kernel of b to the power n minus 1, then the vectors v n s plus 1 through v n r, so these are top vectors of strands of length n. And then we go down in these strands by applying operator b. So then vectors v n minus I j are equal to b to the power I applied to vector v n j, where j goes from s plus 1 to r. And in this way, we obtain all the vectors in the strands of length n. The proof of the Jordan Normal Form Theorem that we're going to present next will follow this strategy. And what we need to prove is that the set of vectors that we obtain as a result of this algorithm will indeed be a basis for the root space U mu. Our algorithm for constructing the Jordan basis is iterative, and it is only appropriate that we will prove the Jordan Normal Form Theorem by induction. We are going to reformulate this theorem in a way that's compatible with this inductive procedure. Theorem. Let B be a linear operator on a vector space U such that b to the power n is a zero linear operator. Suppose we already have a linearly independent set Vij, where I goes from 1 to n and j goes from 1 to s, satisfying b applied to Vij is equal to Vi minus 1 j for I greater or equal to 2, and b applied to the bottom vectors V1j is equal to a 0 vector. So here we already have s strands of length n, and we are given that this set of vectors is linearly independent. Then there exists another set of strands Vij, where now j runs from s plus 1 to r, with the same properties with respect to the action of operator b. So with the same action of b, such that the union, so the set Vij, where j now runs from 1 to r, is a basis of U. Now, in the additional set of strands, the lengths could be arbitrary. Corollary. If we take S to be equal 0, so that is empty set of pre-existing strands, we obtain the claim of part 2 of the Jordan Normal Form Theorem. Without these pre-existing strands, this theorem claims that the space U has a basis that consists of a union of strands, which is equivalent to saying that the space U decomposes into a direct sum of cyclic subspaces. This pre-existing family of strands makes the statement more complicated, but we need this in order to match our inductive procedure for construction of this basis. Let us give the proof of this theorem. We give the proof by induction on N. So the basis of induction is the case when N is equal to 1. So here we are given that operator B is equal to a zero operator on U, which makes sense because here we are talking about our bottom layer. And we have a linearly independent set V11 through V1s. We know that we can complete this set to a basis of U, V11 through V1s, then V1s plus 1 through V1r. Since our operator B is 0 on U, we have that B acting on each of these vectors will give a 0 vector. So this will become the set of strands of length 1. This is precisely what we need to prove in the case when N is equal to 1. Now let us carry out the step of induction. We assume that the statement of the theorem holds for n minus 1. And now let us prove it for given n. So we are given that the set Vij, where I goes from 1 to n and j goes from 1 to s, is linearly independent. In particular, this means that the vectors in these strands at the bottom level are linearly independent. So we get V1j, where j goes from 1 to s, is also linearly independent. Then, applying lemma 1, we get that the set of equivalence classes of the top vectors, v and j, where j goes from 1 to s, is linearly independent in the quotient space, U quotient by the kernel of b to the n minus 1. We can extend this linearly independent set by adding equivalence classes of vectors v n s plus 1 through v n p to get a basis v and j, where j now goes from 1 to p, in the quotient space u, quotient by the kernel of b to the n minus 1. Now construct new strands by saying that v n minus I j is equal to b to the power I acting on v and j for j from s plus 1 to p and I from 1 to n minus 1. Since b to the power n is equal to 0 in u, we will have that b acting on the bottom vectors v1j will produce 0 vectors. Now, applying lemma 1 again, since this set of equivalence classes v and j, where j goes from 1 to p, is linearly independent in the quotient space u by the kernel of b to the n minus 1, this implies that the bottom vectors v1j, where j goes from 1 to p, is linearly independent in u. But then, by lemma 2, we know that if the set of bottom vectors in the strands is linearly independent, then the set of all vectors in the strands is linearly independent. So by lemma 2, the complete set of vectors vij, where I goes from 1 to n and j goes from 1 to p, is linearly independent. Next, consider the space kernel of b to the n minus 1. If we take vectors in the strands that do not belong to the top level, so the set vij, where I goes from 1 to n minus 1 and j goes from 1 to p, this will be a linearly independent set in the kernel b to the n minus 1. And of course, tautologically, the operator b to the n minus 1 is a 0 operator on the kernel of itself. So now, on this kernel of b to the n minus 1, we have a set of linearly independent strands of length n minus 1, and the operator b to the power of n minus 1 is 0 on this space. Now we're in a situation where we can apply the induction assumption. By induction assumption, we can extend this set to a basis of strands in the kernel of b to the n minus 1. So we'll denote this set as vij, where j now goes from 1 to s, and I is less than n. So what do we have now? Now we have a basis of a subspace kernel of b to the n minus 1 and a basis of the quotient space, U quotient by this kernel. By applying our result that relates the basis of the whole space to the basis of a subspace and the quotient space, we obtain the basis of U. Now we have a basis of U quotient by the kernel of B to the n minus 1, so which is the set of equivalence classes V and J, where J goes from 1 to P. And a basis of the kernel of B to the n minus 1, which is the set Vij, where I is less than n and J goes from 1 to S, which is greater or equal to P. So combining and applying the theorem that relates the basis of the space to the basis of a subspace and the quotient space, we get that the set Vij, where now I is less or equal to n and J goes from 1 to S, is a basis of U consisting of strands. And this completes the proof of the Jordan Normal Form Theorem. We see that this proof follows closely the algorithm that we described earlier. Here we are trying to construct strands of length n by identifying their top vectors. To do this, we take vectors at level n of the previously constructed longer strands and consider the quotient space by the kernel of B to the n minus 1. So we construct new top vectors by completing the set of vectors at level n minus 1 to a basis of the quotient space. In this way, we obtain a family of strands of length n. And then we go to the subspace, which is the kernel of B to the n minus 1. Now, by removing the top vectors, we get strands of length n minus 1, which will belong to this kernel. And by induction assumption, we can complete this to a basis of shorter strands. And then reinstating the top vectors that we have cut off from strands of length n, we will obtain the basis of U that consists of a family of strands. Finally, we point out that the sizes of Jordan blocks corresponding to eigenvalue mu are determined by the sequence of numbers. We have dimension of the kernel of t minus mu I, which is less or equal to dimension of the kernel of t minus mu I squared, which is less or equal to dimension of the kernel of t minus mu I cubed, and so on. In particular, the first dimension is the number of vectors at the level 1 in this diagram. So this means that the first number, which is the dimension of the mu eigenspace of T, it determines the number of Jordan blocks. And then the second number tells us how many vectors in this basis do we have on both first and the second level. The third number tells us how many vectors in the strands are on the level up to 3, and so on. We have already seen that from this sequence of numbers, we can derive the length of each strand in this diagram. So the conclusion is that the Jordan normal form of T is unique up to the permutation of order of the Jordan block. We can rearrange the order of the Jordan blocks in the Jordan normal form, but the eigenvalues and the sizes of Jordan blocks for each eigenvalue are uniquely determined by the operator T itself.